Welcome back to the Deep Dive. Today, we are undertaking a really critical mission to untangle the complexities of Azure Key Vault security, identity, and, well, integration.
Right.
For anyone managing a cloud environment, this is where the rubber really meets the road. And for those of you preparing for exams like the AZ-104, these scenarios are, they're guaranteed to test you.
That's absolutely right. Key Vault looks simple on the surface, it stores secrets. But underneath, it's a collision point for governance, networking, and identity strategy. And we are focusing specifically on 15 crucial high-stakes scenarios. We call them the exam traps because, well, they cover these subtle distinctions that catch even experienced admins off guard.
And that leads to production errors, right? 403s or worse.
Or worse, yeah, security compromises. Our goal isn't just to memorize the answer, it's to dissect the why behind Microsoft's architecture.
Exactly. Why does one solution work for failover but just completely fail for administrative control? Or why can't two specific security models coexist? That's the stuff we need to know.
We'll be zeroing in on those critical differentiators. The fundamental conflict between RBAC and access policies, the limitations of managed identities, and the absolute necessity of separating control plane from data plane.
Understanding the scope.
Understanding the scope is everything. It's the shortcut to mastering this.
Okay, let's unpack this. Starting right at the foundation with the most common and I think the most critical hurdle, the authorization models. And the fundamental reason they create this forced choice for every single administrator.
Every single one. The moment you provision a key vault, you are making that foundational decision.
Traditional vault access policies or the newer centralized Azure RBAC model. Right. And this choice, as we're about to see, it's highly restrictive.
Let's start with scenario one. It's a problem we see in, virtually every maturing Azure environment.
A legacy vault.
The legacy vault, exactly. Maybe 5 years old, relies entirely on the traditional vault-specific access policies. Now, the organization has adopted centralized governance. They need PM, right? Privileged identity management.
Just-in-time access reviews.
All of it.
Yeah.
And they demand role-based scoping that's managed consistently across the entire tenant.
Okay, so centralized governance immediately points us toward Azure RBAC. It's the native way to integrate with Entra ID features like KeyM.
Of course.
But here's the trap. The common assumption is that you can just layer RBAC on top. You think, I'll keep the old policies for the legacy apps, and I'll use RBAC for all the new governance, assuming, the most restrictive permission wins.
That is the conceptual hurdle. It's just not how it works.
Yeah.
The reality is that the two models conflict profoundly because they use two completely different authorization pipelines to the data plane.
Two different pipelines.
Completely different. Access policies are the original older Key Vault native mechanism. When a principal presents a token, Key Vault checks that token directly against its own local access policy list. It's a self-contained check.
Okay, so it's all happening inside the vault, so to speak.
Inside the vault. And RBAC, on the other hand, delegates that authorization check externally. When you use RBAC, Key Vault redirects the request to the Azure resource provider, and that allows the resource provider to check against all the standard Azure policies, conditional access, PM status, management group assignments, you name it.
So because they use separate paths, one internal, one external, they just can't merge.
They can't. If you try to run both, the access policies essentially bypass the modern RBAC checks entirely. You end up with this massive governance gap.
So if the security team mandates PM and centralized auditability, you have no choice. You must commit. The vault has to switch entirely to the Azure RBAC permission model.
Precisely. The switch isn't optional for modern compliance. Once you commit to RBAC, you get the full suite of Azure governance. You decommission the local access policies, and you move all your data plane permissions, read, write, rotate into standard RBAC roles like secrets user or key crypto officer.
The core takeaway here, and this is non-negotiable for the exam.
Yes.
A key vault can use only one model effectively for the data plane. RBAC or access policies, not both.
Never both.
But the architectural challenge that creates is immense. How do you flip this switch on a live production vault without breaking everything? This is the fear that keeps administrators up at night.
The fear is justified, and it requires a methodical, low-risk strategy. The first step is not to touch production.
Right.
Instead, you establish temporary shadow vault. This shadow vault must use the RDAC model exclusively. You replicate your secrets into it, and then, crucially, you migrate your identities, your managed identities or service principals, to the new RBAC structure on that shadow vault.
So you're testing everything in parallel.
You're testing everything. Before deployment, you test your critical apps using their new RBAC assigned identity against that shadow vault. It verifies the identity, the role, the network path, everything, without impacting the working production asset.
It's expensive in terms of time, but...
That mitigates catastrophic failures, the only safe way.
Okay, so if RBAC is the definitive model for governance, there must be a compelling reason why access policies still even exist.
There is.
Scenario 5 presents that critical exception. An application must be permitted to read only version X of a secret, but access to any newer or older versions has to be explicitly denied.
And this is where RBAC reveals its limitation. RBAC is fantastic for broad scoping, right? Granting read access to a set of secrets or write access to a whole vault. But RBAC rules apply to the entire resource type.
So all secrets, all versions.
All versions. If you assign the secrets user rule, that applies to every secret and every version of every secret. RBAC just lacks the built-in logic to restrict access down to a specific version number.
So for environments like tightly regulated healthcare or finance, where auditing requires that kind of version immutability, RBAC fails.
It fails the requirement. It forces a deviation. The correct solution here is to revert to access policies with secret-specific scope.
So you go back to the old model for this one specific need.
For this one need. Access policies offer that hyper-granular control. They let you specify GTT permissions only on the specific secret URI that includes the version ID. For the AZ-104, this is a non-negotiable rule. Access policies are the only option for per-secret find control and version-specific permissions.
But that creates what you call the hybrid reality. You have this organizational mandate for PM, which demands RBAC, but then you have this one app that demands access policies. How does an architect reconcile that?
You utilize the separation of the control plane and the data plane, a concept we'll dig into more later.
Okay.
You use access policies only for that single application's data plane access, the reading of that one specific secret version. For everything else, managing the firewall, enabling soft delete, rotating admin keys, you leverage the RBAC control plane rules, often with PM.
So it's a necessary compromise.
It's a necessary compromise. It accepts the data plane conflict for a specific requirement while maintaining governance over the resource itself. It's tricky, requires great documentation, but it's the only way to satisfy both demands.
Okay, let's see the practical effect of this on a running app. Scenario 14. An app service using Key Vault references, that really convenient at Microsoft Key Vault syntax.
Everyone uses it.
And it suddenly starts throwing a generic 500 error after the Key Vault authorization model was switched from access policies to RBAC.
The 500 error. It's often Azure's way of saying, I tried, but the security gatekeeper slammed the door. The trap here is thinking the application reference is smart enough to handle the change automatically.
It's not.
It is not. The app service is using its managed identity, which probably had get permissions under the old access policies setup. When the vault switches to RBAC, those local policies become inert. They just stop working.
But the identity object itself, the managed identity, it's unchanged.
Exactly. And this is the crucial takeaway. Key vault references always use the vault's current authorization model to validate the caller. When the model switched to RBAC, the app service's identity token arrived. The vault checked the resource provider for RBAC assignments and found nothing. The permission just evaporated.
So the fix is straightforward identity remediation, just under the new rules.
Absolutely. The action is to reassign the app service's managed identity with the correct data plane role. You need to assign Key Vault secrets user at the right scope. That 500 error, which masks an underlying auth failure, is just Key Vault requiring the app to present the new paperwork.
That brings Section 1 to a really clear close. The authorization duality is a hard boundary. If you choose RBAC for governance, you have to be ready for the migration and that version control exception.
If you get that, you've internalized the fundamental security model. Now, we can pivot to the mechanism that actually uses these authorizations, managed identities.
Right. Managed identities are foundational to Azure's Zero Trust model. They get rid of passwords and code. But the complexity is in the two flavors, system assigned and user assigned.
And knowing which to use is vital for a resilient architecture.
So let's look at Scenario 3, which is probably the most classic failover trap. A geo-distributed app needs to failover from region A using Key Vault A to region B with a replica Key Vault B.
And the app uses a managed identity to get secrets. The wrong assumption, the trap, is thinking any identity will just travel across regions with the app.
Well, this comes down entirely to the identity type. Let's start with the one that doesn't work.
The system-assigned MI, or SAMI, that's the one that traps people. A SAMI is deeply tied to the life cycle of the specific Azure resource it's created for. A single VM, a single app service. It exists only within that resource, in that region.
Because it gets its token from the regional instance metadata service, right?
Exactly. It is physically bound to that single resource instance. It cannot be moved, shared, or used by a counterpart resource in region B. It's stuck.
So if the app in region A fails over, the new app in region B starts up, tries to use the old SAMI identity, and just fails.
It failed because that identity doesn't exist for it. For any high availability, scalability, or cross-region scenario, SAMI is insufficient. The solution has to be the user-assigned MI, the UIA.
The UMI then is like the trusted chauffeur of the secret world.
That's a great way to put it. A UIMI is created as a standalone resource. It lives at the tenant level, independent of any specific compute instance or region. You create it once, and then you assign that single shared identity resource to the workload in region A and the workload in region B.
So the identity lifecycle is separate from the compute lifecycle.
Crucially, after you create the UIMI, you grant that single UIMI resource identical RBAC rights on both Key Vault A and Key Vault B. So when failover happens, the workload in region B assumes the UIMI, and since that UIMI already has pre-authorized permissions on Key Vault B, the access is seamless, immediate.
That's the definition of identity portability.
And a resilience.
Okay, so UMI for anything involving scale or redundancy. SAMI for simple, single-instance apps where that regional binding is okay.
That's the rule of thumb.
Now let's pivot from portability to sprawl management. Scenario 10. We've got 20 different microservices, each with its own unique set of secrets. The trap, the natural instinct, is to create 20 separate key vaults.
And that is the path to operational debt. Just imagine managing 20 sets of firewall rules, 20 soft delete configurations, 20 sets of diagnostic logs. The administrative burden is massive.
Not to mention the risk of configuration drift, where one vault is slightly less secure than the others.
It increases exponentially. The objective here is centralized security and governance without compromising least privilege. Microservice A must never see microservice B's secrets.
So the solution isn't more vaults.
The correct modern solution is a single shared key vault coupled with multiple user-assigned MIs. You establish one UAMI per microservice, UMI service 1, UMI service 2, and so on.
And then you use RBAC as the mechanism for isolation within that single vault.
Exactly. We leverage RBAC scoping at the secret level. UAMI service 1 gets key vault secrets user permission only on secret A, B, and C. UMI service 2 gets the same role, but only on secret D, E, and F. The separation is entirely identity-driven.
So the vault remains a single, easily governable resource.
And the security boundary becomes the identity assigned to the calling microservice. It's a huge governance win. You maintain least privilege, you eliminate inter-app secret leakage risk, and you dramatically simplify operations.
The lesson is clear. Use identity separation over resource duplication.
Always. And Scenario 13 just reinforces this. We have a requirement to guarantee that an app in a test environment cannot retrieve production secrets even if it runs the exact same code base.
The trap is assuming a config file change is enough protection. Because if the code is identical, a simple accidental change in that config could point the test environment straight to production data.
You need a definitive security curtain that the application itself cannot bypass. And the solution is, again, environment-specific UAMIs.
So walk us through that isolation boundary.
You create UIMI prod and UIMI test. UIMI prod is assigned to the production workload and gets key vault secrets user rights on the production vault. UIMI test is assigned to the testing workload, and here's the key. UIMI test is given no key vault permissions at all, or maybe only rights to a non-sensitive testing vault.
So if the test workload tries to call the production vault, using its identity, UAMI test.
The vault checks the identity against its RBAC list, finds no authorization, and denies the call instantly. 403. End of story.
It's bulletproof isolation. Since the identity is managed entirely outside the app code, the app can't accidentally or maliciously elevate its own privileges.
It's the definitive way to ensure environment isolation. It fulfills that strict zero-trust principle. Access depends entirely on the caller's assigned credentials, independent of the code being run.
Okay, our next major section is about roles. Assigning the right role with the right scope. I mean, that's the cornerstone of least privilege security. We need to dissect the crucial difference between roles that manage the vault and roles that manage the secrets.
The separation control plane versus data plane is the source of endless confusion and, frankly, security breaches. The control plane manages the Azure resource object itself, the vault. The data plane manages the sensitive material inside, the secrets, keys, and certs.
All right, scenario 2. A classic real-world request. A new function app needs to periodically rotate, so modify, and also read a sensitive API key in the vault. The developer asks you for the key vault contributor role. Why is that the wrong role?
That is the deadliest trap in Key Vault. Key Vault Contributor is a control plane role. It grants the principal permission to manage the Azure resource, change networking rules, enable or disable audit logs, add tags.
Critically, it can disable surge protection.
Exactly. It's an administrative role. It grants far more power than is needed for simple secret rotation.
So, if I assign contributor and that function app gets compromised, the attacker can now change firewall rules or disable logging before they steal the secrets.
Exactly. The blast radius of a contributor compromise is massive. For the exam, you have to remember, never use contributor unless the principal is explicitly tasked with managing the vault's configuration settings.
So if the function app only needs to do data plane operations rotation and reading, what are the correct least privileged roles?
If the app needs to read the secret, you assign Key Vault Secrets User. If it needs to rotate, create, or update the secret, you assign Key Vault Secrets Officer.
The distinction is clear.
Very. The Secrets Officer role grants rotation and update rights, but it does not grant access to keys, certs, or the overall vault configuration. That separation shields the vault structure from the application's data handling needs.
Okay, but what about deletion? If the Secrets Officer role permits deletion, which is often needed during rotation, what if the organization fears accidental deletion of the secret itself?
That's a great question. It necessitates a secondary governance layer. Option 1 is a custom RBAC role. You derive it from Secrets Officer, but explicitly remove the Microsoft Key Vault Vault Secrets Delete permission.
Okay.
Option 2, which is architecturally superior, is to enforce data retention using the native feature. Soft delete plus purge protection. Purge protection prevents permanent deletion of the vault or its contents, even by privileged admins, until the retention period expires.
So it mitigates the risk regardless of the role.
It mitigates catastrophic data loss.
Let's refine those control plane roles. Scenario 8. We need a DevOps engineer to manage the KV firewall, networking, and tags. But they must be prevented from reading any secrets or keys.
A pure resource management task?
My first thought might be Key Vault Administrator. It sounds like they're administering the resource. Why is that the wrong choice?
Because Key Vault Administrator is an omnibus role. It's a combination role. It grants both control plane access and data plane access. If you give the DevOps engineer administrator, they can manage the firewall, sure, but they can also read every single secret inside.
Which violates the security mandate.
Completely. The correct narrowly scoped control plane role is Key Vault Contributor.
Right. So Contributor lets them manage the vault configuration settings, networking, firewall tags, but it does not allow secret reads.
Exactly. It doesn't let them touch the data plane. This is a perfect example of how Azure RBAC enforces separation of duties. The network team, with Contributor, handles the security perimeter. The application team, with Secrets User, handles the data within that perimeter. Neither can do the other's job.
It's the security curtain principle. You manage the fence without seeing the treasures inside.
And that significantly limits the scope of damage if the DevOps engineer's credentials were ever compromised.
Okay, now let's take that least privileged role and make it time-bound. Scenario 9. Sensitive secrets can only be accessed temporarily by privileged engineers for troubleshooting. A clear directive for P.
The exam trap here is just consistency. Just as we didn't use Contributor for an app reading secrets, we don't use PM on Contributor for an engineer reading secrets. The mistake is enabling PM for a high privilege role when a lower privilege one would do the job.
The engineer is performing a data retrieval task. That's data plane.
Therefore, the correct solution is PM-enabled Key Vault Secrets User, or maybe Secrets Officer if rotation is needed. You apply PM on the lowest privilege role required for the task. The engineer elevates their privilege only to the data plane, only for an hour, and often only after manager approval.
And PM generates an audit trail of that elevation. But for full governance, what's the mandatory linked requirement? What has to happen after they've accessed the secret?
The audit trail must be complete. PM tells us who elevated and when. But the essential compliance step is enabling diagnostic logging and routing it to a centralized sync like log analytics
To see what they actually
to
did.
see what they actually did, which secret version they accessed, from what IP address, what specific operation they performed. Without that robust diagnostic logging, the PIM elevation is only half audited. You have a huge compliance gap. Both must be present for true zero trust.
Okay, we've covered identity and authorization. Let's address the external factors now. The operational stuff like networking, hybrid connectivity performance that can completely break Key Vault access, even when the identity is perfect.
This is the #1 call we get in production support, the network plane trap. Scenario 4. A VM with a perfectly configured system-assigned MI suddenly starts getting 403 forbidden errors right after an admin enabled a private endpoint on the vault.
And the admin says, my RBAC is right. My identity is right. Why am I getting 403? The assumption is that identity overrides network restrictions.
And that assumption is disastrous. Identity authorization and network routing are independent security gates. This is a critical point. RBAC success does not guarantee network success. A 403 from Key Vault can mean you lack permission or I don't trust the network you're calling from.
Right, so when you enable a private endpoint and kill public access, you're moving the vault off the public internet and onto a specific private subnet.
You are. And if the VM tries to call the public Key Vault FQDN, the request is blocked at the network level and returns a 403. It never even gets to the identity authorization engine.
So the problem is the VM is trying to resolve the public IP, which is now blocked.
Exactly, even though it's sitting in the same VNet as the new private endpoint.
So the solution is purely networking and DNS plumbing. Walk us through the checklist.
You need to confirm 3 things. First, private endpoint reachability. Is the VM in a subnet that can even route to the private endpoint? Second, and this is the most common failure point, crucial DNS resolution. When the VM resolves the Key Vault FQDN, say myvault.vault.azure.net, it must resolve to the private IP of the endpoint, not the public one. This requires linking the private DNS zone -privatelink.vaultcore.azure.net to the VM's VNet.
If DNS fails, the call fails.
Instantly. And third, check your network security groups, your NSGs. Double check that no NSG or UDR is accidentally blocking outbound connectivity to the private endpoint IP or blocking the return traffic.
The lesson is that zero trust demands success at both the identity layer and the network layer.
You have to pass both gates. Now let's step into the hybrid world. Scenario 7. An on-premises ADFS token-based system needs to retrieve certificates from Key Vault.
And the immediate tempting solution is, let's get managed identity to work on-prem.
And that is the biggest conceptual barrier. Managed identity never, ever works outside Azure. It's fundamentally reliant on the Azure Resource Manager and the regional IMDS endpoint to mint tokens. Your on-prem system can't access that internal Azure fabric.
So if we can't use the modern credential-less identity, we have to use a globally recognized alternative.
The alternative is the service principal, the SP. You create it in Intra ID, grant it RBAC rights on the Key Vault, and the on-prem system uses that SP to authenticate.
But SPs usually require credentials, which violates the no long-lived credentials principle.
Which is why the type of SP authentication matters intensely. We use a service principal with certificate-based authentication, not a password. The on-prem system uses the certificate to authenticate, gets an access token, and presents that to Key Vault. It's supported, audited, and the gold standard for secure hybrid access when MI isn't an option.
Password-based SPs are a no-go.
Strongly discouraged, especially in regulated environments.
Okay, let's talk about authentication failure upstream. Scenario 11. An Azure DevOps pipeline using a service principal fails to authenticate to KV right after the SP secret was rotated.
This tests where Key Vault's responsibility ends. Admins waste time checking Key Vault permissions and firewalls. The trap is assuming an auth failure is a Key Vault problem.
But the core principle is that Key Vault trusts the service principal object in Entra ID. It doesn't care about the SP's password.
Exactly. The failure is entirely upstream. When the SP's secret was rotated in Entra ID, the Azure DevOps service connection, the caller, was not updated with the new credential. The pipeline is still presenting the old expired secret to Entra ID.
So Entra ID denies the token.
And the call never successfully presents any valid token to Key Vault. The fix is simple, but it's external. You have to update the SP credential in the calling system in the Azure DevOps service connection.
Right. It highlights the distributed nature of authentication.
It does. Key Vault is just a passive receiver of valid tokens. If the token's no good, the fault is with the system that was supposed to mint it.
Okay, our final operational challenge. Performance under load, scenario 15. A distributed app retrieves secrets frequently under heavy load and gets transient failures, 429 errors.
This is a conceptual trap about Key Vault's intended use. Key Vault is a secure secret store. It's built for security and auditability, not for high-volume, low-latency configuration serving.
It has service limits.
It does. And if an application tries thousands of requests per second, Key Vault will throttle a client. You'll get 429 too many requests errors.
So architecture needs to solve this, not configuration. How does an app implement a defensive design?
It's a purely client-side defense strategy, and it's mandatory for using the Key Vault SDKs properly. 3 things are essential. 1, secret caching. The app retrieves secrets once on startup and caches them securely in memory.
Minimize round trips.
Exactly. 2, retry logic with exponential backoff. For those unavoidable transient errors, the client has to retry, but it must wait longer after each failed attempt, 1 second, then 2, then 4, to give the vault time to recover.
Just slam it with requests.
Right. And 3, conditional refresh strategies. Don't constantly poll for new versions, only refresh when you're alerted or check a lightweight metadata endpoint.
The takeaway is, Key Vault is a security vault, not a configuration cache. Design your apps accordingly.
You have to.
We've established all the component parts. Now let's look at how they integrate in modern zero-trust architectures, specifically with Kubernetes.
Right. AKS. It's a primary consumer of Key Vault secrets. Scenario 6 involves an AKS cluster using workload identity to access Key Vault, where pods authenticate using a Kubernetes service account.
The exam trap here is relying on old tech. AED pod identity is deprecated. What's the modern definitive answer?
The modern standard is Azure Workload Identity. It aligns perfectly with Zero Trust because it uses federation. No secrets are passed or stored anywhere. The identity is derived and trusted.
Okay, can we break down the moving parts of this federation? It sounds complex.
It sounds complex, but it's actually quite elegant. It connects the K8's internal identity to the external Entra ID identity. First, you have the identity, a user-assigned MI created outside the cluster. It gets the Key Vault RBAC role.
Okay, the UIML.
Second, the Kubernetes caller. Within the AKS cluster, you define a Kubernetes service account that the pod uses. Third, the federation link. You create federated credentials in Entra ID. This object establishes a trust relationship, linking the Kubernetes service account to the user-assigned MI.
So it connects the inside to the outside.
It does. And fourth, the authentication flow. When the pod starts, it presents its Kubernetes service account token to Entra ID. Entra ID verifies the federation link and then issues an Entra ID token, which the pod then uses to authenticate directly to Key Vault.
So the Kubernetes service account effectively assumes the role of the UAMI without ever handling a credential.
It's a pure identity handoff. It eliminates the complexity and security risk of the older methods. It's lightweight, secure, and the required blueprint for modern AKS deployments.
Okay, we've discussed everything from authorization to networking. Scenario 12 forces us to put it all together. A high security mandate requires full zero trust, no public access, no long-lived credentials, strict identity-based access, and network segmentation.
This is the checklist that separates a junior admin from a seasoned architect. If you can implement this blueprint, you've achieved Key Vault mastery.
Let's synthesize the components of this comprehensive zero-trust architecture.
Okay, 1. Identity first. Use managed identity, specifically UAMI, for portability. That's your no long-lived credentials mandate.
Check.
2. Network segmentation. Implement a private endpoint for the Key Vault. 3. Network firewalling. Explicitly block all public network access. Traffic can only arrive via that private endpoint.
Right.
4. Authorization governance. Enforce the RBAC-only authorization model to make sure PM works. 5. Administrative control. Implement PM for all administrative roles to ensure just-in-time access. And 6. Auditability. Ensure diagnostic logging is enabled, immutable, and routed to a secure, centralized sink.
That blueprint is complete. But let's end with one final reminder, tying back to the biggest real-world pitfall.
Yes. The final trap reminder. Simply disabling public access is not enough. If you block public access without successfully configuring the private endpoint in the corresponding private DNS zone, you have successfully locked out your own applications with a network 403.
Regardless of how perfect your RBAC is.
Regardless, zero trust means validating both the caller, which is identity, and the path, which is network.
That was an incredibly dense and critical deep dive. For those preparing for the AZ-104 or managing live infrastructure, let's distill this. What are the three most essential, high-stakes concepts to walk away with?
First, the authorization duality. It's RBAC or access policies. RBAC is for governance, PIM, and scale. Access policies are the necessary evil only for version-specific control. You have to know which to choose.
Second, master the identity distinction. UAMI is for high availability and portability. SAMIO is fixed and regional. If you have 20 microservices in one vault, you use 20 UAMIs for isolation.
And third, the fundamental independence of the network plane and the identity plane. A 403 error is ambiguous. Your perfect RBAC means nothing if the private endpoint DNS is misconfigured. Always check the network plumbing first when access suddenly fails.
And finally, I want to re-emphasize the role distinction. Success is in understanding the scope of permissions. Stop reflexively assigning contributor. Differentiate between configuration tasks, control plane, contributor, and data access tasks, data plane, secrets user officer. That single shift in perspective is the biggest security improvement you can make.
Absolutely. The audit trail is your foundation for governance.
So what does this all mean for you, the administrator, moving forward? Since Zero Trust mandates PM and diagnostic logging is required for audit, you have to consider how robust your compliance logging really is. Do you have a plan to meet the architect challenge of recording every single privileged access action taken in your vault for compliance, including the activation of temporary PM roles? That level of granular, reliable, and immutable logging, that is the next layer of complexity you'll need to explore to fully secure your assets. That's it for this deep dive. Until next time, stay secure.